Hey YouTube, it's Dimitri. Today we're going to talk about three kind of interesting topics all layered together from a very practical stance here. So if you're wanting to see things from a quant perspective, more realistically, this will be the video for you. Today we're going to talk a little bit about measure error and measuring issues. So yes, measuring things, that's a lot of what math is. People argue that's physics. It's a whole other tangent. But there's a lot of things we're trying to measure, and there's measurement error in that. The second piece is going to be math versus statistics. So I had somebody mention like, oh, I'm just going to go get a bunch of math degrees. I'm just going to do math. And I'm like, okay. And they're like, that's probably better than doing math and statistics, right? Because statistics isn't really math, and that's not really what quant researchers do. And I'm like, quant research is just statistics, and statistics is, in my mind, just math. Stats and probability kind of go hand in hand, and they nestle into this world of mathematics. That's going to be the second point. And then the third point is going to be, how does corporate politics, damage control, and miscommunication impact and play into the quant space regarding these measurement errors, and some of the issues you're going to face as a researcher, as a quant, as a business person that's using these models. But let's just dive on in here to a few examples, and I'm going to kind of cover these broadly in kind of just these three sections here. So the first point here is going to be measurement or measurement error specifically. And I'm going to do two examples here. I'm going to do one that's just a simple, probabilistic kind of framework here. And that's going to be the coin toss. So I have this website. It's called Practice, mathmammoth.com. It's a coin tosser. It's virtual. And we're going to put in the probability that we're going to get tails and the number of repeated repetitions. So let's just do like 10, for example. And we'll toss one coin 10 times, and you end up with 50-50. That's pretty surprising, to be honest with you guys. So let's toss it again. And now all of a sudden we end up with, the experiment is 70-30. So 70 tails, 30 heads here. And theoretically, I have 50% put in, so it should be 50-50, right? You can see when we're doing this probabilistically, there is a measurement error here. If I ran this experiment just this one time, for example, in practice, and in financial markets and econometrics and in the real world, we often do things one time, and then you have to tell me what that probability is, okay? And I'm going to give you a real world example here in a second. So 70-30 is awful. People are going to say, okay, let's do it another time. 80-20, we got even worse. Okay, interesting. But let's increase the number of repetitions. I often hear the number 30 thrown out there, as 30 is an ample sample size to do some sort of estimation. So we go through and do a toss, 50-50, which seems to be how this tool works on the first shot. 46-53, that's pretty close. But you gotta realize, in your head, you have some expertise, because I'm telling you we're tossing a coin, regardless of what they set the probabilities to. In your head, you're probably thinking 50-50. So when you see 46-53, you're like, well, that's close enough. Close enough for what, right? We're gonna answer that here in a second. Let's toss it again. Again, it's the same results. 40-60. Again, we've only done a couple tosses here, a couple runs here, and we're at 40-60. That seems pretty far off, right? You can only get a value from 0 to 1, 0% to 100%. And you have 40-60. Let's toss it again. 46-53, 53-46. There's obviously a mathematical design here, and based on the sample size as well. So let's increase this again. So I hear 100 is often a really good number. That's ample enough, right? 30, that was kind of sketchy. Let's do 100. So we'll toss it, and we're at 46-54. Again, start thinking in your head, how close realistically is that if you needed to use that for some sort of decision, right? And that's going to depend on the decision you're making here. Let's toss it again. 54-46, 45-55, that's better. And then finally, let's do a couple more, 48-52, 42-58. So that seems to be about how the design works. 44-56 here. And let's just, for sakes, let's do 1,000 and toss this. 50.2 and 49.8. So that's pretty close, seems like. 49.2 and 50.8 again. 53.6 and 46.4. So again, we're only doing a few different simulations, and we're starting to wonder, how close is close enough, right? This is the measurement error that we're having. So let's go back to our diagram here. And the question we want to know is, what is close enough? And more specifically, this is going to be some sort of measurement error. Now, The coin toss, I'm going to tell you, is actually IID. So some concept that we run through, and IID is going to be independent and identically distributed. Now, what this means more or less is that you're pulling from some sort of probability space, so some sort of number space that you have, and that each time you do some sort of, so let's do the coin toss here. Each time we flip this coin, it's independent. It's not dependent on how many runs we had before that. There's no sort of information being passed across the samples here, right? If you do 10 heads in a row, it does not impact that the next toss will be a heads or a tail. Now, the identically distributed portion of this is actually pretty important. What this implies is that it's coming from some sort of distribution. So in this case, you could say it's uniform distribution with 50-50. But we're pulling from the same distribution every time. Now imagine as I went back into those coin tosses and I changed those probabilities, that's changing the distribution of the toss. So like when I did the first toss and it was 50-50, we did that a few times, that's IID. Now, if I do 50% heads tails and then I change it to like 40% heads tails and we swap that and then run some simulations here. So let me do this again real quick. I just want to show you guys, if I run 100 in here and we do like say 40 and we do a toss, we end up with 63-47. Now imagine you don't know if this coin is fair. It's a 50-50 or it's a 45-55 or if it's a 40-60. Like you don't know. If you don't know and you're doing these sorts of tosses, again, as you watch here, the distributions kind of swap around and sometimes they're close, but you're really dependent on the fact that you can do the experiment over and over and over again. And really every time I ran that experiment with 100 or 1,000, I had to do that 1,000 experiment once or twice to get some sort of estimate. But again, we are assuming IID. Now the problem in finance is finance often is not going to be IID. You have a lot of assumptions we need to make often to get to IID, and this is where the theoretical stance comes through, where it's not necessarily a computation of simple mathematics anymore. So this is what I'm going to call stats versus theory a little bit. So tying this idea in here, we'll put this as number 2. The stats versus theory part is going to be understanding, like, is it IID? There's really no simple way we can just say, yes, it's IID. Like, you're going to have to use insight from the business, from the problem, from the issues you're solving to figure out if it is IID, if it is close enough to IID. And I can tell you in finance, we often run into issues and struggles with this sort of concept here. And so when we're starting to go through this now, right, math starts to become very theoretical. It starts to become very much of an art. And why I say this is because you're going to need some business insight. And this often only comes not from a business degree, but this only comes typically from experience. And experience in the sense that you've done essentially that coin toss experiment at a bunch of different firms, for example, or you've done it at the same firm for 10 years, 15 years. You start to understand some of the nuances in the data that were not available through simple data analytics, data testing, data analysis. And finance, the most critical piece of finance is going to be this concept of time. And so as time passes, the economy changes, the dynamics change. There are a lot of complexities that you have to think about, and you can't just simply run some sort of calculation here. So again, the measurement error question is hard to answer, and it often takes some sort of expertise on that. And this also leads me to why statistics is so critically important. So imagine you have some sort of equation. We're going to do linear regression. Y, something we're predicting, is equal to alpha, which you intercept, plus beta 1, x1, plus beta 2, x2, plus, whatever. I don't know how many. Beta in x of n plus epsilon. So what I mean is we have some sort of linear regression. It could just be 1, beta 1, x1, right? And what we're going to do is we're going to create some sort of regression, and we're going to look at fit or accuracy. That is a really naive approach to doing this, but it's there. And this is where p-values come in. So p-values are one of those things that I hear people say, oh, Dimitri, they are absolutely awful. They do not work. Oh, and I'm not going to say which community, but there is a specific set of people out there that are getting trained these days that tend to think p-values have absolutely no value and no meaning. And part of it is stemming from this fact that we're missing the IID portion of this. The experimental design of how the data is going to be collected and processed is part of this main issue here. And so the p-values themselves are critical because what's p-value testing? It's really testing whether your beta 1, which is your coefficient, is going to be equal to 0 or not equal to 0. That's what we're trying to figure out. If it is equal to 0, we can just remove it from the equation. And for those of you that don't understand simple linear regression, we're predicting y, and then your alpha would be some sort of number, let's say like 0.3, and then your beta, which is what we are going to be estimating, or more specifically, what we are measuring. We are measuring the relationship. In this case, let's say, I don't know, beta is going to be, 1.37, and then you have times whatever variable that you put into here, and then you could add, beta 2, beta 3, beta 4, all the way through that. But if we just kept this really simple structure, what I'm trying to figure out is this 1.37, even though it has accuracy, does it meaningfully, in a probabilistic setting, what's the likelihood that that is going to be different than 0? Okay, so that's like the coin toss. We're looking back at this IID kind of function here and thinking to ourselves, I need some sort of tool to do this. It's not a guarantee, right? This is no longer simple math. This is no longer like 10 plus 10 is 20. We can't just churn through this blindly and generate some sort of solution. This is going to be the stats versus theory piece, right? You have to understand the theoretical underpinnings of this because I see a lot from very junior and inexperienced quants and data scientists, machine learning, and, physicists, mathematicians. They tend to go through this exercise of some sort of estimation. And I would like to point out it's not just linear regression. It's machine learning, right? You have estimations of properties, whether they're, hyperparameters. You're doing some sort of estimate and you're trying to get to some sort of relationship that you're trying to, measure, right? We're really measuring to see what it is. Now, when I measure that, the question being is how much measurement error is in that measure? And as I'm trying to point out and show you guys, you have to use your head. You have to look at the problem. It's going to vary for every tool. And there is no simple, silver bullet, like easy tool or metric that solves everything. So let me give you guys a real world example on this. So I work in the auto loan space. I've worked with mortgages. I've worked with credit cards. I've worked with a lot of different sorts of products here. But let's just do a loan example. When we take loans at a very small firm, you often run into lots and lots of issues around just data robustness and proper data sample and size. And so you have kind of two problems here. You have data size, which is going to be, we understand from like this coin toss example that we were looking at, as we were tossing and increasing the number of observations, we converge to more or less the true answer, the right answer here. But when you're a small firm, you don't have a lot of data. So you kind of have two paths you can take here. You can buy industry data, or you can just use your data. Or more specifically, you can combine the two. But the issue, though, is now I know for a fact, again, this is a theoretical piece, these two sets of data are not equal. The way that you run your business, the way that a company runs a business, every firm essentially takes some sort of, I'm going to paint this as a blob, some sort of, we're going to say this is the industry, and it's very high dimensional. And you're going to have, let's say your firm kind of has this weird strategy and plan, and on paper it looks very simple, if this, then that, some simple rules, some credit policy design, something like that. But realistically, your space probably looks wonky like this. And this kind of pinky purple space here is what you're going to be operating in. And your methodology for filtering, processing, and doing loans is going to be a combination of policy and models. So your models are going to make decisions based off of their structural design. The complexity and design of models ends up creating this crazy kind of shape in here where you're not like a nice, pretty square box. You have these weird dimensionalities based on different variables, and model and policy are essentially going to filter the data such that your IID sampling is no longer IID. It is not truly random. Your pricing and strategy teams are impacting and changing how the data is being pulled in, and you no longer have a random sample. So you can already see we're running into issues just from simple how the market and how the world works. This is quite challenging. And if you buy industry data, right, everyone has a different shape, so you can't really depend on the industry's data, and you can do stratifications. So you give a bunch of different attributes, for example, to a data vendor. They'd go out, they find people that look just like you, and they never will, but they look just like you on paper. Because there's too much dimensionality to capture, and they pull all this information, they create a sample, and industry data creates some sort of measurement error. The measurement error here is going to be a large error. So that is something you have to keep in mind when you use that data to develop models or to do test or analysis or review or simple analytics, like what is the average default for this sort of customer, or what is the profitability. You have to realize the measurement error is going to be larger. How large? I do not know. But you have to keep that in your mind. Now, when you use your current data, you're going to end up with the fact that you don't have enough actual data points to do a proper estimation and calculation here. So you have two types of errors, and the size of the error here is unknown. And I say that because we know that these are not IID. So I can't say, like in our awesome coin toss experiment, I can't say, let's increase this. Once I hit 1,000, I toss this, and oh, okay, we're closer than we can be. And you can see we're getting closer in this estimation here. That's not what we can do. We have this vast amount of uncertainty. This is risk. This is called model risk. So this is model risk management, which is model validations at banks and firms. This is model risk. This is a critical piece here. And how a model developer handles this, how they understand this, how much faith they put into this, all determines how they're going to do this. And as an example on this, you have model complexity. And so I tend to favor very simple models for firms and institutions which have limited data. Now, you're going to face the argument, and this is going to be the politics, which we'll get to in a second. This is going to be the politics of the issue, because complex models generate better accuracy. And that's great. That's awesome. That's what the business wants. They just want accurate numbers. Do it, do it, do it. But there's a lot of pitfalls and issues that come into this now because you have more significant model errors. And this goes back to, should you be using industry data? Should you be using your internal data? Should you be using some sort of approach to scale the industry data to match your personal data? Again, these are very theoretical ideas you have to explore and look at and do analysis on. But the politics comes into this of you're going to have people that are going to push you. And almost every person in the world in the finance space, especially the businesses, love complexity. They love AI and ML, anything that is hand-wavy, complex design. Firm after firm I've been to, they love to see the complexities of this. Even when a simple model will blow a complex model out of the water, they don't like that. They want to keep it very, hand-wavy. They want to feel like they're doing something important here. So this is a critical issue here, and the politics is going to be, how do you convince people on what type of model do you need? And let's be honest, there's not a simple model and a complex model. There is going to be a simple model. In our example, let's say this is logistic. You might go down this spectrum. You might have something like GBM, and it might keep going down into, like random forest. And then it finally ends up with something like a neural network. And depending on the design, the structure, the complexity of this problem, you're going to have to sell the politics of this, convince people to use these sorts of models, knowing in the back of your head as a model developer, there is going to be measurement error. And I don't know the exact amount of measurement error. And so you're trying to figure out where on this spectrum you need to be to balance the model error and the politics of this. And so an example is, let's say you had some loans come through the door, you had some model you're measuring, and we're going to be measuring loan performance. And you have this sort of table here, and it tells you this is how the model should perform. And you say, okay, at time 1, it should be 1%. So this is 1%. And you don't have very many loans at this point, and they come through the door, and you have, total loans of 53. And then you have bads, which is the number of loans that are bads, and you convert this into the more or less the prediction here. And what you end up with here is you end up with 2 loans that went bad in that first month. Okay, so this is what you're supposed to be. You do 2 divided by 53, and our prediction here is going to be the 1% that we wanted. And then our actual bad rate was going to be 3.77%. Okay, so it's on this chart, probably 3.77 is right here. It's 3.77. And your dot, let's change colors, is right here. So you say, okay, we have this. And now you have the business losing their absolute minds because, rightfully so, this error is huge. Okay? And so what ends up happening now is now you say, well, if we would have just lost one less loan, so this would have been 1, this would have been 1.89%. It's still greater than 1%. So to actually beat the model prediction, I would have to have 0. Now you start to see with this, with the measurement error, with the sampling issues, with the fact that we're not IID, in this real world example, you're gonna have the business freaking out often if they don't fully grasp all this concept of data, sparsity, and measurement error. I can explain the data issues here quickly and easily, like, oh, we would have to have 1 or 2 loans and whatever, but often explaining IID and not random sampling, and we have a theory and we have a process, and also, by the way, there's a bunch of servicing departments that impact how defaults are handled and how they're classified and the timing of those. That all drives and impacts your model. Now, it happens when somebody comes up with this idea here and they present this chart, and they say, hey, your error is going to be off by 377%, right? And I've had this happen. They say, this is the model error is 377%, and the world is completely melting down, and we need to do something, and we need to get a new model, and the world's gonna change, and I don't know what to do, and the model development team's not doing their job. And you're sitting there like, this isn't even a valid analysis, right? This is what is the politics side of this. And this is where I'm going to tell you guys it's extremely hard. This is politics. But it's a very large struggle, and it's very real. And it's something I'm not going to say is necessarily like, oh, everybody should know this, and I'm going to wave my hands and everyone should just, be smart and know all this. They don't. But this is the piece that you're going to have to cope with. And the way to actually handle this in most situations is to calmly, don't lose it. I just want to scream at times when these happen. So dealing with the politics, the best thing, one, is just to explain in a nice, calm manner, explain the issue with the analysis, and do a PowerPoint. I know this is a lot of work. I know it's frustrating to make these. I find the business sides and even quants themselves understand these better when you sit, you get all your thoughts, you put them together, and you put them on paper, and you actually explain the issue at hand. Now, I'm going to tell you, make it very simple, make it very easy, because this is critical. Okay, so explaining the issue is going to be part of this. The second thing is going to be accept life. Often you are going to end up in situations where people lose it. You realize there's no way to salvage this, right? If I can't explain this, especially when I start to go back into this framework and I'm explaining all these different slides I gave you guys, and I'm going through the theory and the IID, what ends up happening is people's eyes just like glaze over, they tune out, they don't want any involvement, and they just go away. Sometimes you just have to accept this is going to be the decision that is made. So they will knee-jerk reaction. They'll want you to do full redevelopment. It'll cost 3 months of time, maybe 4 months of time, depending on model complexity. It could be up to 12 months of time, multiple employees, a full rigmarole. I would highly recommend trying to go the explanation route, which is the first step of this. But when all is lost, sometimes you just have to accept the facts that this is what we're going to do. You've made your piece, you've made your argument, and then the second point is just going to be just accept it. This is something that's very hard to do from the quant space here. But in simple summary of this, right, the measurement issue, the measurement error is hard to do. That's what I want to point out. There's always some sort of measurement error. You're never going to have perfect data. And in finance, your data is often filtered through corporate decisionings and businesses and firms, from competitors as well. So that drives market competition and supply and demand and a bunch of other things. So measurement error is the first real big topic here. The second one is math versus stats. And what I wanted to point out with this is just that there's a lot of theoretical underpinnings of statistical theory that need to be applied to the math, right? We're just doing math. Like, even if you take an average, you can't just take an average and say that's the average. You have to understand there's going to be some measurement error. You also need to look at the theory statistically on some sort of test that might help you, make an adjustment or an issue with that. Stats has a lot of different sorts of adjustments. And then finally, the third one's going to be the politics of handling these situations. Math, theory, and logic is great for quants, but that's not what gets the job done, unfortunately. Even when you go through explanations and you tell people how to do things and you provide PowerPoints and presentations, you do a bunch of analysis, often the time you have to respond might be a day, and then people are making decisions and they're running and they're moving, and you don't have time to do the presentations. I've been in this situation before. The way to handle this is just trying to explain it. Whiteboard is the second best option if you don't have a PowerPoint. You can't do that. Trying to get to the basic core of this. Try to get in front of the issue. But unfortunately, right, it doesn't matter often if you're right or wrong. It really matters what the business think, what the quants think, what the teams and departments think. It doesn't matter who's right, who's wrong. What's going to end up happening in the long run is you're going to make decisions. And making decisions often happen quickly, and you have to get there fast. So communication is a key part of this, and the politics play into that, and how you handle that kind of juggle that is also a critical point of that. So anyways, I hope you enjoyed this video. If you found it helpful, don't forget to like, share, and subscribe, especially on LinkedIn. And as always, until next time.